Okay, so the first lesson was just absolute extrema. So even in the homework, if they ask you for relative stuff, I hope you just skipped right over it. Let's just remind ourselves the difference between absolute and relative extrema. So let's say you have a graph, right? And it looks like this. Okay? You would then classify this point right here as your absolute min. Right there. This point. Right? And your absolute max, of course, would be up here at this little corner thingy. Right? Absolute max. But what about the points that are maximum in their region, right? So this would be like a relative max, or our book calls it a local. Max. And then we have basically a relative minimum right here. And what about those endpoints? Well, technically, this point on the far right is also a local minimum. You might say, I disagree. That's not a relative or local minimum. But it is, because in its region, it is the lowest point around. So this is a relative min. Okay, there's nothing to the right of it. It's true, but you have to argue that it is the lowest point around. Okay. That means that over here, we should probably also classify this point as a relative min as well. Okay? So don't be surprised that this absolute min, I've also labeled it relative min. Okay? Relative means just in its own vicinity, it's the lowest point. And it is true that this is the lowest point in its vicinity and on the entire graph. Right? So if you're the poorest person in America, you're also the poorest person in your neighborhood. Do you understand what I'm saying? If you're the lowest income of everybody in your neighborhood, or everyone in the U.S., you're also the lowest in your neighborhood.
Probably don't have a neighbor.
Well,
probably don't even have an income.
I don't know how to pick a better analogy than that. I guess we could do the absolute max, right? We know that if we assume that people with authority have power, right? If we say the most authoritative person in the U.S. is Obama, let's just say, because he's president, he has the most authority delegated to him, technically. You could say that since he is the absolute highest authority in the nation, he's also locally the highest, right? In the White House, for example, he's the highest, most authority in the White House. You see what I'm saying? So if you're an absolute extreme, you're also a relative extreme. That means this top point, we can also declare that to be a relative max as well. So if you're looking for absolute extrema, it suffices, it's enough to find the relatives, the relative extrema. If you want to find the President of the United States in your living room, just invite all leaders to your home. And the president qualifies, he's a leader, right? He would show up in your home, assuming he wished to be there. Okay? All right. Bad analogies, but some things get labeled double, is what I'm saying. All right. So the question is just, can we find all the points, green and blue? And so what I did was I picked, for my first problem, a polynomial, and there was no given domain. So let's just do y equals x cubed plus 2x. Let's actually do negative x cubed plus 2x minus 4 for our first one. And it's just find the extreme values. And we're going to do the local and absolute, unlike Friday. Okay, so what you might want to do is actually start with some pre-calc, okay, because you kind of already know that a graph like this one is going to have end behavior something like this. That's kind of a head start. You already know there's an arrowhead going up on the upper left. You know that there's an arrowhead going down on the lower right. You already know that about every cubic that's got the negative cubics look like this, don't they? All right. So start with that. Let's go ahead and take the derivative, because I don't think we're going to have any endpoints, you know what I mean? We don't have to look at endpoints here, because there's no endpoints. So let's just jump straight to y prime. Y prime is negative 3x squared plus 2. And if we set this equal to 0, and try to solve it, we get x equals plus or minus the square root of 2/3, also known as plus or minus the square root of 6 over 3. Okay? So we got 2 points where we have horizontal tangents. There are horizontal tangents at these 2 points, for sure, because we set y prime equal to 0. We should also ask, can y prime be undefined? So also ask, can y prime be undefined? But in this case, we don't need to worry about that. Why not?
Because all polynomials, all real numbers is the domain.
Yeah, polynomials are hungry creatures. They do not have any domain exclusions, so we don't need to worry about y prime, since it's a quadratic polynomial, being undefined. It's not going to happen. There's no denominators, there's no radicals. In this case, no. Okay, so we have exactly 2 candidates for extremes. They're right here. The annoying thing is finding the y values. It's super annoying. So how am I going to get the y values? I got to plug those back into the original function, right? Okay, so here's what I'm saying. I know that there's at negative rad 6 over 3 and at positive rad 6 over 3. Those are where my extremes are. I already know where the arrowheads go on this graph. So what I'm going to do is I'm just going to assume that this thing goes down, up, down. I mean, what else would it do? I'm thinking it goes down, up, down. I don't think it crosses through the origin. I think it goes through negative 4. But my point is this, listen. If there's an arrowhead going up here and an arrowhead going down here, and one of these is a min and one of these is a max, the only way for me to even connect these thoughts is if this one's the minimum and this one's the maximum. There's no other way to connect them. There's no way that's the maximum. Because it has to go down, up, down. So I think I've already figured out which one's which, if that makes sense. All right, so let me relabel this since I colored over it. So I already know there is a relative min at x equals negative root 6 over 3, and there's a relative max at x equals positive 6 over rad 3, just judging by the end behavior of this graph. If that's all they want from me, I'm done. If they want me to plug in these and get the y values, I will, but I'll be very bitter about it. And I will use my calculator, because I'm too lazy and too sloppy to get these right. I also don't think on the AP test you would be plugging in root 6 over 3 and cubing it, although I could be wrong.
They're not that cruel yet.
Not quite that cruel, right?
Not yet.
Okay, so I have plugged in weird stuff before, but I don't recall plugging in a radical into a cubic. That's awful. So, but feel free to do it. To get the y values, you'll see in the back of the book. They probably used a computer, right, to do their work, and then they make you do it by hand, right? Okay. Let's go on and look at a totally different graph. Oh, by the way, you guys understand that this graph has no absolute max and no absolute min, right? There's no highest point of all, so we're talking relative today. Okay, let's go on to this problem, this next one, and it is same instructions. Find the extrema relative and absolute, and the one I picked was y equals 1 over x squared plus 1. You might recognize it. It's actually the derivative of arctan, right? Not that that's really important, but just kind of interesting little fact. Okay, so no endpoints. Don't really know what the graph looks like. I can make some assertions. For example, you can just do some basic chapter 2 stuff to help you understand the function a little bit better. Isn't it true that if you go limit as x goes to infinity, this goes to 0?
Yeah.
Okay. And if you go limit as x goes to negative infinity, this goes to 0. Right? You guys with me? In other words, we believe that this is a horizontal asymptote. Y equals 0 is a horizontal asymptote. We have this graph diminishing onto the onto the x-axis as you go out to the left and the right. Also, isn't this an even function? What does that mean? Okay, so it's got y-axis symmetry. How can we tell by looking at it?
Well, all alpha thugs are going to be negated x and stuff.
Yeah, if you change x to negative x, nothing's going to happen, right? If you change x to negative x, that means the left and right sides of the graph are exactly the same. Okay, it's an even function. So f of x and f of negative x are identical. So it probably looks something like this. You know what I mean? I'm just kind of sketching. I don't know for sure, but it probably looks something like this. Or maybe it's down underneath, you know? It also has no roots. There's no x-intercepts, because the top can never be 0. There's no vertical asymptotes, because the bottom can't be 0. It's actually a pretty simple graph. It's just diminishing behavior. And if you plug in 0, you get 1. So I think this is right at 1. I think I already know the answer. I think there's a relative maximum at 0, 1. You guys see what I did? Just kind of sketched it out using some old facts. Question?
Yeah, how did you find that there was a asymptote at x equals 0?
Y equals 0?
Y
Well, yes, because I did the limit as x goes to infinity, and I got 0. That right there proves that there's a horizontal asymptote, at least on this side. And then I did a negative infinity limit, and I got 0 again. That means this side behaves the same way, which makes sense because it's an even function. It has symmetric behavior. So I know these peter down to 0. I know that this can never yield a negative number. There's no way it's going to ever give me a negative number, so I kept out of these two quadrants. And then I knew that we plug a 0 to 1. I'm pretty sure this is the graph. Yeah.
So do the limits to negative and positive infinity have to match to
No.
say it's a horizontal asymptote?
No, they do not.
No?
If this had come out to 0 and this had come out to 82, there'd be 2 horizontal asymptotes.
Okay.
If this had come out to 0 and then been infinity, it still would have had a horizontal asymptote. On the right, the graph would approach 0. It's a good question. When you're doing your test corrections for the first chapter test, don't try to convince me that there's a horizontal asymptote because these two agree. Okay? If this is 0, it's a horizontal asymptote, regardless of what this limit does. You do not need agreement on that. What was your question? Okay.
I'll ask later if it's...
I'm pretty sure the answer is 0, 1. Now let's do some calculus. Okay, so let's look at the derivative of this. So y is x squared plus 1 to the minus 1. Right? The derivative, just bring the negative 1 down and take away a power. Don't forget the chain rule, multiplying by 2x. In other words, y prime is negative 2x over x squared plus 1. And this should be minus 2 power now. So this is squared. Okay, let's look at the derivative and just see that it really confirms what I believed originally. Does this derivative ever equal 0?
Yeah.
Yes. Y prime equals 0 if what? X equals what?
0.
0. Okay, that means we have a horizontal tangent at x equals 0, just like I suspected in my picture up above. Okay, plugging in y gives me 1. Y equals 1 over 0 squared plus 1 is 1. So there's a horizontal tangent at 0, comma 1. See? There's a horizontal tangent at 0, 1. Because the derivative is 0 when x is 0. could this ever be undefined? That's a very important question that people forget about. Look at this. Is it possible for this to be undefined? No. Then we can skip that phase of searching for extrema candidates. So we can skip that phase. I'll just make a little note in green that I'm skipping that. Y prime cannot be undefined. So we're done searching. We got a horizontal tangent at 0, 1. Now we just need to verify that it really is a max and not a min. This is really important. Horizontal tangents can actually they come in 3 flavors. Okay? Listen, just because, this is all about proof, okay? Just because you found a horizontal tangent does not mean you found a maximum. It could mean you found a minimum, or even what's called an inflection point. Let me just try to show you. You could have a graph like this, and there's a horizontal tangent there, because it's a maximum. You could have a graph that looks like this, and you have a horizontal tangent there because it's a minimum. Or you can have a graph like this, and you have a horizontal tangent here because the graph can't decide if it wants to keep going up or down, and it decides, okay, I'll just keep going up. So it goes up, flattens, goes up. So just saying that there's a horizontal tangent is never sufficient to state whether it's a min or a max. See? So now what I need to do is try and convince the reader that it really is a maximum. And the graph doesn't count. The graph is just my scratch work. That's not proof. It's not proof of anything. Okay? Okay, so I'm going to finally make my argument. 0, 1 is the absolute max, and it's a relative max, of course, because why? What's a convincing argument to prove that this is the highest point on the graph?
The slope changes from positive to negative.
Okay? Yes, you could convince me using slope. This is kind of a 4.3 idea. But you could try to show me that all the tangent lines on this side are rising, and all the tangent lines on this side are falling. That makes it a maximum point, and not a minimum. Do that. Anyone have a different idea? We're trying to be clearly stating that it's not just an extreme value. It is a maximum, not a minimum. How do you show that? I could think of 3 ways. I could say what you said. I would like to show that it rises here, it falls here. I could do that by plugging in -1 and +1 into my derivative. Okay, which means if I get positive, it's going to be rising on this side, and if I get negative, it's going to be falling on this side. Okay? Or I could find the y coordinates of any 2 points, one on this side and one on this side, and show that they are physically lower than this point. Okay? And the third way is I can show that this graph is bent downward in this region. That's a little ahead of our class. So I'm going to actually go with Hugh's suggestion that we test the derivative over here and the derivative over here real quick. Let's plug in -1 into the derivative and +1 into the derivative. Let's see what happens. Y prime is equal to, okay, -2 times -1 over -1 squared plus 1 squared. What does this come out to?
-1/4 or 1/4.
It's 2 over 4.
I'm just kidding. 1/2.
It's half, right? When x is -1. And y prime is equal to -2 times 1 over 1 squared plus 1 squared, which is -half when x equals 1. So what I'm saying is if you're over here at -1, this graph is sloped upwards, and if you're over at +1, the graph is sloped downwards. And you could just argue this. Since f prime goes from positive to negative at x equals 0, x equals 0, x equals 0, 1. Erased too much there. 0, 1 is a max, let's put it that way. 0, 1 is a maximum. Since it is the only candidate, it is also the absolute max. Is the absolute max. It's such a simple problem, but it's really hard to defend it, you know? You really need to convince me that it's got a horizontal tangent here, that the graph went from rising to falling, and then that makes it a maximum, not a minimum. And there are other arguments you could have made too. You could have talked about that horizontal asymptote. And if the graph is going to approach it, it has to go down on both sides. So it has to be a maximum. There's many ways to do it, but this is one way. Okay, let's go on and talk about a radical problem. So what about this one here? Same instructions. Find extremes, right? Find the extrema. And it's y equals 1 over the square root of 9 minus x squared. So this is getting a little bit harder now. So the first thing you might want to ask is, are there endpoints? Does this thing have endpoints? It's getting a little tricky now. There are only select values of x that even work here. I think we have natural boundaries in this problem. You guys know what I mean by that? Let's take a look at the domain. That's not a calculus idea, it's a pre-calc idea, but it's important to us. Okay, so let's take this, let's find the domain of y equals 1 over square root of 9 minus x squared. Let's take that 9 minus x squared, and normally I would take a radicand, you know, and I would set it to be greater than or equal to 0. I cannot even have the inside of this thing equaling 0 because it's on the bottom. So I need to be very strict. This needs to be positive, period. It can't be 0 because it's on the bottom, and it can't be negative because it's inside a square root. Okay, so how do you solve this? Well, you can write it as x squared is less than 9. Can you square root both sides of that?
Yes. Yes.
You can, but you need to stay away from that plus or minus idea. Okay, when you're doing an inequality, square rooting an inequality like this, you square root the left side and it's absolute value of x. You square root the right side, it's 3. And then you try to understand what this means. So what does absolute value of x is less than 3 mean? Doesn't this mean that x is less than 3 and x is greater than negative 3? It's like that double inequality thing. In other words, this means that x is something between negative 3 and 3, is what it means. The other way to do it is, I'll show in my work in blue, you could also have factored this into 3 minus x and 3 plus x, drawn a number line, and tested values, and you would have found that this is true, and the outsides are false. Here's an alternative way to get that domain. But why is this so important? This is super important because we now know that there are natural boundaries to this problem. There's no such thing as, you know, x equals 4 on this thing. Okay, now we can look at the calculus. Let's take the derivative. So y is basically 9 minus x squared to the negative half. And we're trying to find y prime. Y prime is negative 1 half 9 minus x squared to the minus 3 halves times negative 2x. Don't forget your chain rule. In other words, it's x over 9 minus x squared to the 3 halves. There's your derivative. Now let's ask our classic 2 questions. Can it be 0? Can y prime ever equal 0? Yes, if x equals what? 0. Okay, so we have a horizontal tangent at 0 for sure. Can y prime be undefined? Y prime can be undefined. Remember what this means here. This means x over the square root of 9 minus x squared cubed. In other words, we're still restricted between negative 3 and 3, right? Y prime is undefined if x is greater than or equal to 3, or x is less than or equal to negative 3. But it turns out this is supposed to give us, candidates for things. But this isn't going to matter because that's not in the domain anyway, right? We found the domain earlier to be between negative 3 and 3, and now we're getting these, like, not discontinuity, or non-differential points, but they're outside domain anyway. So nobody cares about that. So we need to skip this phase and just focus on this right here. X equals 0. X equals 0. That's our only candidate. And he falls between negative 3 and 3, of course. All right. So now we need to understand what's happening at 0. So the function is y equals 1 over the square root of 9 minus x squared, right? There's actually a vertical asymptote right here and here. That's just basic pre-calc. This function goes to infinity if you plug in, like numbers really close to 3 on either side. And we know that at 0, at x equals 0, we have a horizontal tangent. By the way, that means y is going to be, what's y going to be? 1/3, right, 1/3. So at the point 0, 1/3, we got this graph touching right here. So there's kind of two possibilities. It's either the purple, because this is an even function again, by the way. So you can see the y-axis symmetry. It's either the blue or the purple. Can someone help me decide? Because it makes all the difference in the world. Either I'm going to declare 0 and 1/3 as a minimum or a maximum.
What's the original function?
Let's go back to the original functions right here. Does it have roots or not? No roots. Okay, then it's the blue one. See? There's no roots. No x-intercepts. Look at the numerator. The numerator can't be 0. So there's so much thinking going on, It's like one thing after another, just when you think you're done. This is the graph. Okay, so let me ask you a question. Should we, next time, just graph it and look at it? Is that fair? I don't think that's very fair, right? Newton knew how to do this problem, and he knew how to sketch the graph based on his calculus understanding, right? And here we are, graphing stuff on the screen and looking at it and answering calculus questions. It's a little bit backwards, historically. We should be able to sketch based on the function and the symmetry of the function, and there's no roots, and there's asymptotes there, and then a little bit of calculus to show where the minimum point is, and then sketch the graph. It's not supposed to be the other way around. We're always looking at the graph and interpreting. So, long before the day of graphic calculators, this might be one strategy they would have to graph, look at the derivative, that sort of thing. But there's a lot going on there. Okay, so we have an absolute minimum at 0, 1/3. And that's our only point. Absolute min at 0, 1/3. And of course, that's also a relative min, isn't it? The local min. If you're an absolute leader, if you're absolute minimum, you're also a relative minimum. Okay, let's go on and look at a piecewise function. I know this is a lot, but the variety might help. How about this one? How about negative 1/2 x squared minus 2x plus 4 for x is less than or equal to 0. And let's do x cubed minus 3x plus 5 if x is greater than 0. Let me just make sure this makes sense. I actually wanted to do a 4 here as well. There we go. Okay, so this is also a mix of pre-calc and calc, okay? So what we have here is a parabola on the left, and it opens down, and it's joining up with a cubic on the right that's going to go upwards. So it's going to look kind of like a weird hybrid thing. What happens at x equals 0 is the question. Because when two graphs come together, like a parabola, oops, that's not a parabola. That is like a weird thing. Okay, when a parabola, right, meets up with a cubic, any number of things can happen. You could have a cusp there, you could have a corner there, well, not a cusp, you could have a corner there. You could have like just a hole in the graph, right? It's possible that these don't even meet up. You know what I mean? Maybe this piece is like higher up. You could have a jump discontinuity, all sorts of things. There are no domain restrictions, like no endpoints. So we're just going to have to jump right into the calculus, but we have to be kind of careful here. Okay, so let's go ahead and move all this over. All right, so I'll sketch it as we go. Why don't we take the derivative first, since we've never done the derivative of a piecewise function together, I don't think. How do you take the derivative of this? You can literally just take the derivative of the parts. So you take the derivative of the first part, and then you take the derivative of the second part. Okay. But be careful with the domains. These stay, but you have to throw out the equals. So these are now strict less than and greater than. There is no equals here.
Why is that?
Why is it? Because we don't even know if these graphs meet. So how dare we talk about the derivative there?
Okay.
You know what I mean? At 0, where they're supposedly coming together, they might come together and there might be a corner.
Okay.
Or they might not come together at all. So how dare we include this in our derivative? That can't be right. So we have to look at x equals 0 separately later. Okay? But this will give you for everything else. Okay, so now let's go ahead and look at when can this be 0. Okay, so y prime can be 0 if x is equal to what? There are three answers to this. -2, or 1, or -1. Good. So there are 3 horizontal tangent situations here. Let's find the corresponding y values real quick. What would y be if x was -2? Be careful, you got to go back up here now. Right? Okay, so if you're going to find the y value, you have to always go back to the original function. Okay, so let's plug -2 into the one that will accept it. This second one will not take it. It will only be this one. So -half times 4 is -2 plus 4, basically plus 8. So isn't that 6? Okay. You guys got to check my arithmetic. This is where it all falls apart for me. Okay. Plugging in 1 and -1. If you're going to plug in -1, you would be plugging it into this function. But listen, this function will take it, but the derivative came from the other piece. So we could actually throw this value out. Okay, we're not even going to need it because that's in case you have the whole cubic. It represents this point. But we're planning on not even graphing this side because we're not graphing the cubic on the left at all. So we're going to toss that value. We don't need it. It's out of domain. That point is out of domain. There is a -1 for x, but it belongs to this function, not this one. Okay. But x equals 1 is interesting. And what's the y coordinate for that? Remember, you have to plug it into this function now. See? Only this Okay, so here's what we have. We have the point negative 2, 6, which is actually the vertex of the parabolic piece on the left. And that parabola obviously has a y-intercept of 4. You can see it right here. I'll circle it in yellow. It has a y-intercept of 4. Can you guys see that yellow? Y-intercept of 4. Okay, and then the other point that we found is the point 1, 2. That represents one of the local extremes on the other function. So 1, 2 is this point. Now this is the right side of a cubic, right? And cubics typically look like this, in red there, see? So this must be the minimum point of that cubic, see? A lot to think about. And it too has a y-intercept of 4. You can see it right here. They both have y-intercept of 4. Okay, so that looks like a cubic, but it's actually a marriage between a parabola and a cubic. See it? And I think we can declare pretty certainly that our absolute max, I'm sorry, our relative max is at negative 2, 6. So I'll just go over here and label these. This is a rel max, and this is a rel min. And these are my final answers down here. And I don't need to find absolute extrema because we don't have any here. The arrowhead going down and up prevents it. What's new on this problem for us, maybe, is that when you take the derivative of a piecewise function, you just do the parts, but leave off the actual values. Do we have any reason to believe that 0 might be a candidate for extreme value? Probably not, right? Do we have any reason to doubt that he is a candidate for an extreme value?
Because they both meet at 4. So
They meet at 4. Yeah. We know that the other root for this red graph is on the left. So this graph actually goes up and then back down, the red one, if you kept straight drawing through. And this one is just probably going down forever. So I can't imagine how that could be a max or min. There's no way that could be a max or min. Yeah.
So if there's no domain restriction, does that mean there's never going to be absolute extrema?
On a polynomial, actually, let me think about that for a second. That's a very absolute statement. If there's no domain restrictions, then we have no absolute extrema. Is that what you're saying?
Yeah.
No, that's not true. Just think of the basic y equals x squared graph, right? Y equals x squared has no domain restrictions, but it has an absolute minimum. Absolute minimum. Good question. Or you might say, like, y equals sine x, right?
Yeah.
It has all real numbers domain, but it has an infinite number of absolute maxes and an infinite number of absolute mins. Those are good questions, though. I like your thinking. Okay, and then the last one I wanted to do was an absolute value. What would this graph look like? What would that look like? That's going to be a really strange graph. Oh, what does it say? It says y equals absolute value of x minus 1 plus absolute value of x plus 2. On a problem like this one, I don't think I would do a whole lot of calculus because working with the absolute values is tricky. Derivative of absolute values is just a tricky ordeal. Okay, you have cusps and you have corners all over the place. So what I would recommend you do is just make a table. Okay, so let's make a quick table. I'm interested in values near 1 because something interesting happens near 1. You know, if this was just the graph of y equals absolute value of x minus 1, and x equals 1, we get a corner. And also negative 2 is interesting. So I'm just going to run values from negative 4 to positive 4 and just do them all. Okay, just negative 4, negative 3, negative 2. I'm just going to build a long table here. Negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. Just so we get kind of the full effect. All right, so what happens? If you plug in negative 4, you get 5 plus 2 is 7. If you plug in negative 3, you get 2 plus 5 is 7. Is that right? No. Negative 3. You get 4 plus, 4 plus 1 is 5. My arithmetic is bad. Let's plug in negative 2. It's 3 plus 0 is 3. Did I do that one right? Yeah. Okay, let's plug in negative 1. That's 2 plus 1 is 3. Interesting. Let's plug in 0. That gives you 3. If you plug in 1, it gives you 3. If you plug in 2, it gives you 3. Interesting. It is an interesting graph. If you plug in 3, you get 7. No. Wait. What do you get? 4. Wait, 5. Hold on. This is the part I can't do. 2. Is it 7?
It's 2, 5.
2, 5. Who said 7? Somebody else said it. Oh, I just heard someone say 3 and I just wrote it down. That's the only one I didn't actually try. I did mess up on another one though. Okay, let's plug in 3. 7. Is that right now? All right, what's the next one? 9. Okay, so I'm just curious what this graph looks like. Let's see. All right, and then for the y-axis, I'm going to need to go all the way up to 9. That's good enough. Okay. So if you're out at negative 4, you're up at 7. If you're at negative 3, you're at 5. If you're at negative 2, you're at 3. If you're at negative 1, you're at 3. If you're at 0, you're at 3. If you're at 1, you're at 3. If you're at 2, you're back up at 5. Oops. And if you're at 3, you're at 7. Yeah, Big Dipper with too many stars. And then 4, 9. So here's what's going on. You have this graph. I think this is probably the first time some of you have sketched this before. Has anyone ever drawn one like this before? It's kind of a fun graph. This is actually the line right here, y equals 2x minus 1 is what it is. And this is obviously the line y equals 3. And this is the y equals 2x plus 1 line is what it is. Okay? But they all kind of got glued together into this weird graph. And I wouldn't really want to do a lot of calculus with this. I just look at this and say, where are my extrema? Well, everything between negative 2 and, what is it, 1. I have a relative minimum and an absolute minimum for all those points. So I just put rel and absolute min at all points, one second, from negative 2 is less than or equal to x is less than or equal to 1. So it's kind of a special case, and there's no absolute maxes on here at all, no relative max. Question?
Yeah, isn't the y, or the first linear line that you kind of separated into negative 2x?
Oh, that's what I meant to write. Thank you. This is the line negative 2x minus 1. You can, by the way, you get those lines by doing, just take away your absolute values completely, and you get 2x plus 1. That's this line. And then if you assume that x is greater than negative 2, but less than 1, then this gets reversed, but this, you can just take the absolute values away. So this would be 1 minus x plus 2, which is like 3. And from this side, you're assuming that x is negative 2, so you'll need absolute values. In other words, you just flip these around and remove the absolute values. So you have 1 minus x plus, and then this, if you're way out here, this becomes negative x minus 2. And you get this line, negative 2x minus 1. So, but that's a little confusing. I thought, let's just make a table, plot it out, and you can tell, oh, you got your absolute relative minimum at all those points in there. So, kind of an interesting one. Okay, I think I gave you enough variety to help you with the homework. You only have a few questions there. Due tomorrow, okay?